crude oil that is pumped out of the ground is not ready to be just immediately used as a fuel in a car or a truck. Instead, crude oil contains a variety of different substances. And that's why it's called crude oil, because it is a crude mixture of various compounds. And so on one end, you've got light gases, the lightest of which, natural gas, can definitely be used as a fuel. On the other end, you've got hydrocarbons that contain dozens of atoms of carbon and hydrogen. And some of them are referred to as asphaltenes. They're even solid at room temperature, and indeed, by the name, they are used as a constituent in asphalt for paving roads and tarring roofs. Now, if you took any of this material and pumped it directly into a car, it would clog the engine, the lighter hydrocarbons would explode. We need to separate out the hydrocarbons that will serve as the octane powered fuel that we put into our cars. And so the first step in refining crude oil into something that's useful at an oil refinery is a process called distillation. And so distillation of crude oil in a refinery happens in a series of columns. And the first thing to understand is that it is a physical separation process. It is not a chemical reaction. That comes later in the process, but here we're just separating the various hydrocarbons physically, not chemically. And so what happens is, and we can see it in the diagram here, the crude oil is heated, and so what we find is in the distillation column, the lighter materials, the methanes and other light gases, go up the distillation column through a series of trays and then sent out. And then the heavier molecules are work their way down through the distillation column and then are either removed or sent to a reboiler and then on to a second distillation column or a third. And so in each column you have more and more separation of the various hydrocarbons from each other, which are then isolated and removed and taken to different parts of the plant where they're processed for various purposes, like gasoline for engines, oil for engines, jet fuel, asphaltenes are removed for use in paving of roads, and the like. And so you can see a detailed description of this process. The same diagram is in our textbook, as well as others, that helps give you a little bit better understanding. That can be found on page 118 and 119 of our textbook. So in our first example of this physical separating process, we're described that there's an oil deposit that is a crude oil mixture, and these are percentages by moles. It is 7% pentane, 33% of the isooctane, and 52% cetane, along with 8% asphaltene. And so we've got the various molecular formulas for those provided for us. So the asphaltene we're going to model as this 38 carbon and 18 hydrogen, although it's really more of a mixture, so that's kind of an average measurement that we'll use. So, of course, in the problem we're asked what is the percentage of each component by mass, using our need know, how solve approach. So we know all of the percentages by moles, and so now we want to figure out what those mass percentages are. So what we can do here is we can assume that we have 100 kilomoles of the crude oil mixture. And if we make that assumption, then we know that we've got 7% pentane, which means we have 7 kilomoles of the pentane. We also then know that we've got 33 moles of the isooctane. We've got 52 kilomoles of the cetane, and then we've got 8%, so 8 kilomoles of the asphaltenes. So the C38H18 we'll use to model that. So then we can take each of these and multiply them by their molar masses. If I know the molar amounts and I know the molar mass, then I can convert these to mass amounts, since that's what I'm looking for here. So in the case of the pentane, I have a molar mass of 72 kilograms per kilomole. In the case of the isooctane, we have a molar mass of 114 kilograms per kilomole. For the cetane, it's 226. Let's try to make that look like a 0 up there. There we go. And then finally, for the asphaltenes, we have a molar mass of 474. So then if we multiply all of these out, we'll get the mass amounts in this 100 kilomole sample. So here we get 504 kilograms of the pentane. We end up with 3,760 kilograms of the isooctane. We've got 11,800 kilograms of the cetane. There we go. And then finally for the asphaltenes, we've got 3,790 kilograms. So then we can add these together and get a total mass, using our significant figures rules, of 19,900 kilograms. And so if we know the total, and then we know how much of each of these we have, if we just divide each of these by that total amount, we can get the percentages by mass. So if we go through and do that, we find we've got 2.53% of the pentane, we've got 18.9% of the isooctane, we're at 59.3% of the cetane, and then the asphaltenes make up 19% by mass of this mixture. So there are different contexts when we need the percentages by moles versus the percentages by mass, and so this is a way that we can convert from one set of measures to the other.